Okay, so for the free version of the software, I'm limited to 15-minute videos, which tells me that I should probably finish this one in this video. Anyway, so here we have a nice simplified expression for the electric field due to a single little itty bit of charge on this ring. Okay, so this is the electric field in the x direction only. We don't care about the y direction, so this is the x component of the electric field due to a single charge. Now I'm basically ready to do some calculus. I'm ready to take an integral. So can I not have that at the same time? Here we go. So to get the total electric field in the x direction, I need to sum up all of the little itty bitty pieces of electric field also in the x direction, which means I need to integrate kx dqi over a squared plus x squared to the 3/2 power. Now, the question is, what's constant? Well, what does it mean that I'm integrating over a ring? Well, I'm taking this little bitty piece of charge and then I'm moving to the next, to the next, to the next, to the next, and so on, going around in this circle. Well, a is always a constant because that's just the radius of the ring. X is a constant, right? This distance from the center of the ring and the point P, that's a constant as well. So actually, I can take out the entire denominator, yeah, and k, of course, is a constant, and x is a constant again. So really, this simplifies quite nicely to kx over a squared plus, that should be an x squared to the 3/2 times the integral of dqi. Well, if I'm just summing up all of the little charges, add up all the charge, I get the total charge. So this can be written as kx q, the total charge, divided by a squared plus x squared to the 3/2 power. Let's take a look. Oh, look at that. That is exactly what I was expecting to get here. This is the electric field at a point P from the center of a ring of charge, right? So center of the ring, some x distance away from the center of a ring that is uniformly charged with charge Q. Done. That points in that direction to the right. Okay, so that took a little less space than I gave myself. But anyway, so your assignment, your group work was to solve this problem, is to take a disk of radius r that has uniform surface charge density sigma, and I want you to calculate the electric field at a point P that lies along the central perpendicular axis of the disk and a distance x from the center of the disk. So what that means, I'll start you off with a little picture, right? So you have a disk of positive charge and it's uniform. And it's got some radius r, big R, and a surface charge density sigma. So the total charge on it, right, this is the total charge divided by the area. So that's Q divided by the area of a disk is pi r squared. So if I wanted to solve for capital Q, I could, but I'm given sigma. And I want to know what the electric field is at a point P, so from here that lies along the central perpendicular axis, so that's what's going in and out of the page or the screen for you, and a distance x from the center of the disk. So I'm going to change, my perspective a little bit, kind of rotate this a little bit to the right. Here's the disk of radius r. Here's my x-axis. X. Here's the center of the disk, and I want to know what the electric field is at some point P, some distance x away from the center. Now this looks remarkably similar to the problem we just did for good reason, because you need to use the result of the problem we just did. Now for this type of problem, I'm just going to get you started, because since I'm not here to help you in class, That's right. What you're going to do is you're going to break this up into little pieces, right? So we have a surface now. Now, whenever we have a distribution, a uniform distribution of charge, we basically want to go down in dimension when we break it up into pieces. So I took my ring, which is basically a one-dimensional thing. It's a line that turns in on itself, and I broke it into little tiny pieces, in like basically 0 dimensions. Now, a 2-dimensional thing like a disc, I want to break it up actually into rings. So here is a little ring. Centered. So let's select that one. There we go. Okay. So now here's my total disc, right? And I've got a little random ring in here. This ring has a radius A, just like in the last problem. It's got a linear charge density lambda. But I can say, right, so this little piece of a ring has charge dq, which is equal to, well, I'll get into that in a second, so that's a little complicated. And I already know what the electric field is due to a ring at point P. So I already know that. I know the dE. So basically, I'm starting now with this result, right? This one right here, except this part is all stays the same, but now instead of a capital Q, now the charge on my ring is a dq, and I'm going to have to play with that a little bit and then integrate. And I have to make sure, actually, right, remember this A was the radius of the ring, right? That's A, the radius of the ring, which is not the radius of the entire disk. That's capital R. So that's R. Okay? So the next piece of the puzzle that you need is what is dq. That's a hard thing. Well, if you've never done it before, it's hard. Okay, so dq is, right, the charge density times the area. But what is the area of this little ring? Well, the area of this ring, because it's so thin, I'm going to say that the thickness of this thing right here, I'm going to call that dr, right, because it's a little tiny piece in the radial direction. And the circumference of that ring is 2 pi a, okay? So this dA can be written as the circumference, 2 pi a, times the thickness, dr. Okay, then I'm going to do one more change that will help hopefully make things make more sense. Instead of calling this A, because A implies a constant, this is no longer a constant, right? We're going to sum up all of the little rings of different radii, right? So I don't want to use the letter A anymore because that's just not a solid number. That's going to change as I add up the electric field due to all of these little rings, starting with one really small one at the center and getting bigger and bigger until I get to the last ring that has a radius capital R. So now I'm starting to see where my integral is going to look like, right? I'm integrating over dr. So I plug this dq into my electric field here for Q. And, right, A we've turned into R again. X is a constant, K is a constant. So work on that. Hopefully it won't be too bad. And then your homework is actually to take the same expression. Here's the result that you should get, so you know what to look for. Is to take the same expression and then to take the limits as you go really, really far away from this, and we'll see what it looks like, and as we get right in the center, what it looks like. I think those were the two limits that I had you do. Okay, so good luck. I'm always around by email mostly. I'm not sure how tomorrow's going. I should be around tomorrow I should be there for office hours if all goes well with the health of my family. So good luck, and I will see some of you tomorrow, and I will see the rest of you on Monday.